Hello everyone. In this video, I'm going to do question 29 from section 15.3, which asks to evaluate this integral given in Cartesian coordinate by converting it to polar coordinate. So what you have to remember is that to change an integral from polar coordinate to from Cartesian coordinate to polar coordinate, you have to apply three changes to your integral. First thing is write your D in polar coordinates. So write your region in polar coordinates. That's the first step. Then the second step is to change the integrand by plugging in r cosine theta for x, r sine theta for y. So when you do that, that's the second thing. The last thing would be rewrite dx dy or surface element in polar coordinate. Dx dy in polar coordinate is going to be r dr d theta. Okay, those three steps we have to do first, and then when we are in polar coordinate, try to evaluate that iterated integral. So for us, the first step starts with writing our region in polar coordinate. Let's see what is that region. So it says it is all x and y such that y goes from 0 to this number. So y goes from 0 to root 4 minus x squared. What about x? X, which is the outer variable, is going to from 0 to 2. So we have to see what is this region first and then try to find boundaries for my new coordinates, which is polar coordinate. Okay, let us see. Y equals to 0 is y equal to 0, so that's that part. X goes from 0 to 2. What about this guy? It says y, let me just write equality. When you're trying to find a region, you try to find what are the boundaries and then put them together, you will get the region. So it is equal to 4 minus x squared. Okay, if I square both sides, and then I bring x squared to the other side, I notice that this is equation for circle with radius 2 centered at origin. So basically I have but it's not the whole circle because y is going to be positive now. So it is just upper semicircle. What about other boundaries? So y is from here to this, so this is y. What about x? X goes from 0, it says goes from 0 to 2, so I have from 0 to 2. So my region is exactly this part. Okay, now that I have my region, I can try to rewrite my region in polar coordinates. So D is going to be in terms of r theta. So let's see first the easy one. Theta goes from 0 to cover this part of circle. I need to go from 0 to pi over 2. So theta goes from 0 to pi over 2. What about r? R, you have to consider the radial time this time. So r is going to be bigger than or equal to 0. R is always bigger than or equal to 0, but this number, if you plug in r sine theta, r cosine theta in this equation, what you will get is r squared equals to 4, which is r equals to 2. So basically my r variable goes from 0 to 2. So that's my region. That's my very first step to convert an integral to polar coordinate. Okay, then I can rewrite this integral now in polar coordinate. First thing would be rewrite the boundaries in r theta variables. So my r goes from 0, oh, sorry, r goes from 0 to 2, theta goes from 0 to pi over 2, and in my integrand, this is second step, I have to plug in r cosine theta for x, r sine theta for y. That's my integrand, and now time to change the surface element in polar coordinate. Write the surface element dy dx in polar coordinate. As I wrote here, it is going to be r dr d theta. So that's the integral I want to evaluate. Now you can simplify this up here. I have r squared cosine squared minus r squared sine squared. I can factor out minus r squared, and cosine squared plus sine squared is equal to 1. So I have this thing here. Now I have an iterated integral written in polar coordinate. I can try to evaluate the inner one first, then the outer one. Here what you notice is that I have an r squared there. So if I put new variable to be r squared, du is going to be 2 r dr. I have r dr here. I can write this as half of du, and this is e to the power u squared. And then I have to change the boundaries. So if r is 0, then u, plug in here, 0 squared is 0. If r is 2, then u is going to be 4. So I have to go from 0 to 4 in my new variable u. So then antiderivative of, sorry, this should be u. This should be, so e to the negative u. Antiderivative of e to the negative u is negative e to the u. I have a half there, so I put this guy there. Then going from 0 to 4, t theta 0 to pi over 2. And then evaluate this thing at 4 and 0. So basically this is 0 to pi over 2. It is negative half e to the negative 4 minus my negative half e to the 0 d theta. So this number here now is constant. It is independent of theta. And I can integrate that part, and I'll get, for integration, I'll get pi over 2, and the rest is going to be half minus half e to the negative 4. So basically, it is done. You can simplify that, but it is done. So just quick wrap up here. What I did was I just tried to apply these 3 steps when we go from Cartesian to polar coordinate. First thing is rewrite your region, your boundaries in polar coordinate. Second thing is change your integrand by writing r cosine theta and r sine theta for x and y. And writing the surface area in polar coordinate, dx dy, you have to write r dr d theta. So to see what is the boundaries in polar coordinate, I have to draw the graph, and I noticed that description is very easy. I found and formed the iterated integral in polar coordinate and evaluated the integral. Thank you for watching this video.